Hello, welcome. Today, let's try to solve a Leetcode problem 862, shortest subarray with the sum at least k. So we are giving an array nums. So inside the nums, there will be numbers. So the numbers will be the positive and negative integers. And we are also giving an integer k. We need to return the length of the shortest non-empty subarray of nums with a sum of at least k. If there's no such subarray, we're gonna return -1. So the subarray is a continuous part of an array. So let me explain the problem. So for the first example, we have a num1 inside of the nums. So the k is 1. So the shortest subarray is still 1. So we're gonna return a 1. So for the second example, even we use 1 minus 2, it is 3 is less than 4. So we cannot find such subarrays. So we're gonna return a -1. And for the third example, we have 2 minus 1 and 2. So 2 plus -1 plus 2, it is 3. 3 is more than and equal to k. K is equal to 3. So we're gonna have a length of 3. So we're gonna return the 3. Yeah, because the length of the subarray is 3. Yeah, I think the problem is easy to understand, but it's really difficult to think about a good solution. We might think of sliding windows directly, but actually it didn't work, because for sliding windows you have to use on square time complexity, but the n is 10 to the power of 5. It means it didn't work. You have to use on times complexity or on log n. Yeah. So for sliding windows, for example, we have numbers like 2 minus 1 and 2. Yeah, we find this is okay, but how should we shift the sliding windows? For example, this is let me just try a little bit about this example and then go to the whiteboard to explain my solution. Because for this problem, I'm going to use an ON solution. Basically, it is a monotonic queue. So for example, we have an array like from 2 minus 1, 2 and 1. If we directly use the sliding window, for example, 2 minus 1 plus 2, it is 3. 3 is more than equal to 3. So the sliding window is 3. Yeah. Now we're gonna check. So for our sliding window, the R pointer will go to the right pointer will go to 1. Yeah, but we don't need to go to this one. Why? Because we're gonna check the minimum. Yeah. So the minimum is 3 at the moment. Now what we're gonna do? We're gonna shift to this number -1. Yeah. So now -1 plus 2, it is less than 3. Yeah. It is less than 3. So what we're gonna do? Yeah, we're gonna shift maybe to the next one. It is number 2. But actually, this is not the right way to solve the problem, because inside the array, it is not monotonic increasing or monotonic decreasing. So we can never solve the problem like using a sliding window directly, because we never know it is always decreasing or always increasing. Yeah, and we don't know how to shift the left border and the right border. And for this problem, actually, there's some intuitions from the title. We're gonna check the shortest subarray with the sum at least k. So we're gonna check the subarray sum problem. So what is the subarray sum? So it means, we're gonna use a prefix sum to solve the problem. If we can use a prefix sum for each of the nums, so for the prefix sum, if it is increasing or decreasing, maybe we can solve the problem. Let me put it in the whiteboard to explain this solution. Yeah, so for example, we're gonna have a prefix sum. I'm gonna use a PS. So inside of the prefix sum array, I'm gonna have some numbers inside. Yeah, so the numbers doesn't matter because the prefix sum is still, it's not increasing or decreasing. It is not monotonic. Yeah, maybe let's just have a check. So we're gonna check, let's check the title. So we're gonna check the minimum sum, at least k. So we're gonna check the sum should be at least k. So how can we keep the window? Yeah, the smallest window and the sum should be at least k. So for example, we have some numbers. For example, this is my first number, and if I were to get a if I were to get a prefix, because it is a prefix, currently it is a prefix sum. So this is my first number, it is index 0. This is my second number, index 1. If I were to get the prefix sum, I want to get the maximum sum. So I'm gonna use this one minus this one. Yeah. So the second number minus the first number. So I'm gonna have the largest prefix sum. Yeah. It means something is gonna be increasing. So if this is increasing, if the next one is still increasing, if this is not a possible answer for the second one, maybe for the third one, the index 2 may be a possible solution. Why? Because if it is increasing, this is fixed, and this is this distance, and for the next one, the distance will be much bigger. Yeah, so this means we're gonna prepare a increasing queue, monotonic increasing queue. And for the monotonic increasing queue, we can always find the right solution. Yeah, let me prepare a more detailed example. Yeah, so for example, inside there are nums, inside the prefix sum, there are nums. So the first number is here, and the second number may be higher, and the third number may be higher still. Yeah, but we are not sure this prefix sum is monotonic, increasing or decreasing. We are not sure. Yeah, but maybe for the first numbers it is increasing. What about if the fourth number, for example, it is decreasing? It is like this. Yeah, but it is bigger than this index. This is the index 0, 1, 2, and 3. So for index 3, it is a little bit bigger than index 1, but it is smaller than index 2. Now let's analyze the problem. Yeah, so is this index 2 useful or not for our solution? Yeah, because currently for 0, 1, there's no possible answers. This is still too small. And for index 2, it is still too small. But now, when it comes to index 3, do we need to use the index 2? Yeah, and we don't need to use. Let's analyze why we don't need to use the index 2. Because currently, 2 is not possible, but 3, it is still less than 2. It is bigger than 1. So we are sure 3 is not possible, right? Yeah, because 2 is not possible. 3 is even less than 2. So 3 is not possible. But for the next number, we are going to check, is this 2 useful for our solutions? The answer is no. Because, for example, next index is the answer. For example, next index is 4. 4 is much higher. Yeah, maybe this index 4 minus the index 0 is the answer. Yeah, but do I need to use this index 2? No, I don't need to use it. Why? Because if I have an answer according to the greedy algorithm, normally the answer should be the index 4 minus index 3. Because index 4 minus 3 would be still bigger than index 4 minus 2. Because index 4 minus 2 is here, but index 4 minus 3 is here. You know the distance, it is bigger. And also, the distance between 3 and 4 is much smaller than the distance between 2 and 4. Yeah, so this is why we gotta keep a monotonic increasing queue. So instead of decreasing queue, we're gonna keep a monotonic increasing queue, because increasing queue can always use the greedy idea to find the right solution, because currently this 3 is not useful. Maybe there are still, this 2, this index 2 is not useful. Maybe there are also some numbers. Maybe there is something bigger and bigger. Yeah. So when it comes to 3, similarly, all these numbers is not useful according to the idea I analyzed, because if I have a bigger number, this 3 would always be the right solution, because it is always close to the index 4, and the absolute value is always bigger than these areas. So this is why we're gonna use the monotonic increasing queue. Yeah, and this problem is really hard compared with the maximum sum, maximum sliding window. I forgot the title. It is a maximum sliding window problem. Yeah. So it is we need to keep a fixed window, but we need to check the maximum numbers inside the window. So for that problem, because it is a maximum, we're gonna use the monotonic decreasing queue. Yeah, but for this problem, while we transform the nums to the prefix sum, we're gonna keep a monotonic increasing queue because we always use this number to minus the first number. We always get the maximum. That is why we're gonna use the monotonic increasing queue, and this is also the greedy idea. Yeah, so if this is possible, so currently the index 4 minus this index 0, so the result is a bigger number. If this is possible, what I'm gonna do, I'm gonna take this number with this index out of my queue, because this is still a possible result, but maybe greedily I'm gonna check the next index 1. Maybe this is a possible result. I'm not sure. Yeah, so I'm gonna take this out and compare with 1 and 4. Maybe from index 1 and 4 is a possible solution. So what I'm gonna do, I'm gonna update my result. So before the result is 4, because from 4 to 0, it is 4. Why? It is not 4 minus 0 plus 1. It is just 4 minus 0 because currently we used the prefix sum. So for example, for the prefix sum, my first number is 0, and currently I have 1 and 2 and 3. Yeah. So actually for this index, it's also the same, 0, 1, 2, and 3. For this index 3 minus this index 0, actually it is the sum of these three numbers. It is just before 0. Yeah, so this is why currently this index 4 minus 0, it is 4. Now, maybe index 1 is a possible result, so result will be updated to 3 because it will be 4 minus 1. And all these numbers will not exist. And maybe this is also a possible result, 3 to 4. So we will update the result. Maybe the result is just 1 because 4 minus 3, it is 1. Yeah. So this is basically the idea. First, we're gonna change the nums into the prefix sum because we're gonna use the monotonic queue and we use the greedy idea to solve the problem. And second, we're gonna use the monotonic increasing queue. Yeah. If you already think about the prefix sum and the monotonic increasing queue, basically you can solve the problem. Now let's go back to the code editor to finish the coding. Now let's together to finish the coding. Let me delete these areas. So we're gonna keep a monotonic increasing queue. Yeah, let me prepare the variable like the monotonic increasing queue. Yeah, just to analyze the problem easily. So I'm gonna use the result. So because I needed to return the result. Yeah, let's check if I also needed to prepare a prefix sum. Yeah, let me first prepare the prefix sum. So it's gonna be the list of accumulate with nums, and I'm gonna prepare an initial. So the initial should be equal to 0. Why? Yeah, as I explained earlier, maybe for example this 1 and 2 may be a possible result if this k is 3. Yeah, so I'm gonna prepare a 0 because so for this numbers, the prefix sum 3 would minus this 0, and then I got the sum of 1 and 2. So here I'm gonna prepare an initial to be 0. Yeah. Now I'm gonna prepare the monotonic queue and result. So it's gonna be the queue for the monotonic queue, and the result gonna be infinite numbers because for the result, if there is no such result, I'm gonna return a -1. Yeah, so I have to prepare a result as the maximum. Now let's try to use the template of monotonic increasing queue to solve the problem. I didn't write any monotonic increasing queue. Yeah, because I write a lot of monotonic decreasing queue and monotonic increasing and decreasing together. But for this problem, basically, it is just monotonic increasing queue. So I'm gonna use for R n in enumerate with the prefix. Currently, we don't use the nums anymore because it has already transformed to prefix, because we're going to use the prefix to solve the problem. As you can see, maybe this is also a DP problem because prefix is basically a DP. So it is a DP plus monotonic Q. Yeah. Now let's try to check. So for R and N, you enumerate the prefix. First of all, we're gonna check. Yeah, I call it pop and append. Yeah, this is the first step. So for the pop and append, basically I'm gonna check the monotonic Q if it exists, and I'm gonna use the prefix. I'm gonna use the prefix with the monotonic Q with the last index. So actually, this is the monotonic increasing Q with -1. So this is the index because I start the index inside the monotonic Q. Why? You can also try to install numbers, but for this problem, we're gonna check the sliding windows. Yeah, we just care about the windows, so we don't need to we don't need to store the numbers inside the monotonic Q. So we just need to put the index because index is easier to solve such problems with the result of a sliding window. Yeah. So if this number inside the let me check. So if this number is more than my current number is n. Yeah, let's prepare an example. So if my prefix sum with this index, so for example, currently the prefix sum is 3. Yeah, inside the monotonic Q with the number is 3, but my current number is 4. So 3 is more than 4. Yeah, so if 3 and is more than 4, I need to pop. Let's check if it is okay. 3 and 4, it is increasing. I need to pop, but it should not be okay. So if 3 is normally, yeah, because this is increasing, I don't need to pop. So it means if 3 is less than, yeah, if 3 is less than 2, so this is decreasing. I need to pop because I need to keep it increasing. So instead of more than, I need to change it to smaller than this number n. Yeah. So for checking the monotonic, if we are sure about it is a monotonic increasing Q, and for check this one, it is bigger or smaller, we can try to use examples. For example, the last number inside the monotonic Q, it is 3. 3 is less than 2. I need to pop out instead of append. If I append, it is decreasing. If I pop out, maybe the first number gonna be 2, the next number gonna be 3 or 4. It will always be increasing. Yeah. Now I gonna monotonic Q dot just to pop it out. So after pop it out, I need to append. Yeah. So for the monotonic Q, should append the index. As I explained, I gonna prepare the index inside my monotonic Q. So this is the first step. So for the second step, what are we gonna do? For the second step for this problem, we're gonna check the result. So let's try to check the result. So if the monotonic Q exists, and let's still use the prefix with let me check. So if the prefix with the monotonic Q, let me copy this one. Yeah, so currently we're gonna use the left side. If I gonna use the left side monotonic increasing Q 0, it means it is the smallest number. Yeah, so my current number gonna minus the smallest number. If it is more than and equal to k, so I can update my result. So what is my current number? So my current number is just prefix r. Yeah, because I loop through to the index r to minus at the head of the queue, it's gonna be the smallest number. Yeah, if it is more than and equal to k, what I gonna do? I gonna update my result. So the result is needed to be the minimum with the result, and here we're gonna use the r pointer minus the monotonic increasing q with 0, because this is gonna be the index. We don't need 2 plus 1 as I explained earlier, because this is the prefix. This is the prefix nums. It is not nums itself. If it is just nums, it is not prefix, we're gonna plus a 1. Yeah, since it is a prefix, we don't need 2 plus 1 as I explained for this example. Yeah, actually this one minus this one, it has already been the result. If we use index 3 minus index 0, so the length is still 3, it's our result. So we don't need 2 plus 1 from here. Let me update. Yeah, let me check if I need to do anything else. So we need to pop out from the left side. So monotonic q dot pop left. Why? Because if we find a solution, for example, from here, we need to take it out because this is not be useful anymore, because we have already updated the result. For the next one, we take it out and check the next one. Maybe this is a possible result. So we're gonna check this one. Yeah, if it is still a possible result, what we're gonna do, we just take it out and check the next one. The next one is here, so we're gonna check this one. Yeah, this is why. Now I think I'm gonna have a return for the result. I think this is basically the entire code. There's not so many lines of code, but it's really difficult to think about the solution. You have to practice a lot. Let's try to check if everything is okay. So I'm gonna prepare a prefix sum, and the start will be 0. And now the monotonic q and result. So I'm gonna first check the monotonic increasing q, and then I'm gonna check the result. The r minus this is 0, I'm gonna update my result. Yeah, this means I need to return the result if the result not equal to infinite. Else it's gonna be a -1, because according to the problem, if there's no such answer, it's gonna be return a -1. Yeah, let me check if it works. Oh, there's some problem. Yeah, let me check. This is a -1, and the result should be 1. If this is result not equal to the infinite, yeah, let me just have a check. Normally the monotonic q would be really difficult to debug. The second example is okay. Yeah, it means my result is always -1. It means something is wrong with my main function. Yeah, it means I didn't update the result from here. So while the monotonic q and the prefix with the q less than n, if this is a 3 less than 2, I'm gonna pop out the 3 and put 2 inside. Yeah, so for the next number, if it is 3, I'm gonna yep. If 2 is less than 3, if this 2 is less than 3, yeah, if this 2 is less than 3, inside of the monotonic queue, if it is 2 and this current number is 3, I'm gonna pop out the 2. I don't need to pop, I just need to append. This means the less should be more than, yeah. So I really analyzed something, but actually I analyzed wrong. Yeah, actually we need to use the examples. Let's try to use the example 2 and 3. So inside the monotonic queue with prefix, it is 2, and my current num is 3. Two is less than 3. Yeah, if this 2 is more than 3, I need to do something. So currently I don't need to do it. So 2 is less than 3, I need to append it inside. Yeah, now let me just run it to check if it works. Yeah, as you can see, it works. So for analyzing the monotonic increasing or decreasing curve, we have to use some examples. Sometimes you might make a mistake. Yeah, I think that is okay. Basically, you can try to use this kind of method to avoid making such mistakes. Now let me submit it to check if it can pass all the testing cases. As you can see, it's pretty fast and it passed all the testing cases. Now let's analyze a little bit about the time complexity. And this is just a for loop. And inside the for loop, we used the monotonic queue technique. So we still used a while. So here is a while, here is another while. So here I believe we should use a while. As I explained for the example, we cannot use if because the sliding window is not fixed. It can be bigger and smaller, and we need to update the result. And even we use the to while loop actually for the queue, we just have one operation of pop it inside and one operation of take it out. And one operation of pop it out and one operation of append and one operation of pop left. So we don't need for each element at most we have 2 operations. So in total, for all the for loop and while loop, it is still on time. Yeah, so you need to analyze why it is like that. Because we are using the monotonic queue, we avoid so many elements. So for example, inside the elements, inside all these areas, we don't use it. We've already popped it out. And this is why it is so fast. Yeah, and I have to say this problem is up to now the hardest monotonic queue problem. And for the maximum sliding window, it's gonna be the easiest monotonic queue problem. If you solved both problems, or if you learned both problems, normally you can practice all the monotonic queue problem because that kind of difficulty, the level of the difficulty for other problems is just in between of this problem and the maximum sliding window problem. Yeah. Thank you for watching.